welcome to Chemical Equilibrium. My name is Dr. English. Today we're going to focus on Le Chatelier's principle, specifically looking at changes in concentration. So we're going to talk about an overview of chemical equilibrium, Le Chatelier's principle, concentration changes, some walkthrough practice to make sure that you can see how to do these, and then finally some Regents practice questions at the end. Overview of chemical equilibrium. When a chemical reaction begins, there are only reactants and no products at all. So for example, we have methane and water as water vapor producing hydrogen gas and carbon monoxide. And at the very beginning, we only have methane and water vapor. As time progresses, the concentration of methane and water vapor will decrease, causing the forward reaction to slow down. The concentration of hydrogen gas and carbon monoxide over time will increase, causing the rate of the reverse reaction to increase. So we are considering that this is a closed system. When we use some of our reactants to make products, obviously our reactants are going to decrease and our products are going to increase. If this is a closed system where nothing can escape, if we have a bunch of products at the end and we can go backwards, we have the ability to go backwards, the amount of products, which are now too much, will decrease as we go backwards and make more reactants. This slowing of the forward reaction and speeding up of the reverse reaction continues until the rates of the two reactions become the same. At equilibrium, the concentration of the reactant and products remains constant. The figure below summarizes the process of attaining chemical equilibrium. So like I just said, in the beginning we have only reactants, and the amount of reactants over time as they combine together to make products will decrease. At the same time, at the beginning, we have no products. But as those reactants come together to make products, the amount of products over time will increase. At equilibrium, the rate of the forward and reverse reactions will become constant, and we'll see this as a flat line in our graph. As with physical equilibrium, it is important to remember that no reactant or product can leave the closed system. If a precipitate, which we know is called a solid, is produced, or a gas is formed in a system that is not closed, equilibrium will not be reached. Let's talk about Le Chatelier's principle. Any change in temperature, concentration, or pressure on an equilibrium system is called a stress. Le Chatelier's principle states that if a stress is placed on a system at equilibrium, the system will shift the equilibrium in a way to relieve that stress. A new point of equilibrium is achieved once the stress is resolved. Chemical reactions can shift in two directions. A reaction can use reactants to make products, or it can use products to make reactants, reversible reaction. When a reaction uses reactants to make products, the reaction is said to have shifted in the forward direction, otherwise known as to the right or in favor of making products. When a reaction uses products to make reactants, the reaction is said to have shifted in the reverse direction, in other words, to the left or in favor of the reactants. When a stress is placed on a chemical reaction at equilibrium, the reaction can shift right, shift left, or not at all. Let's focus on changes in concentration. In a chemical equilibrium, if the concentration of one substance is increased, the reaction will shift to use some of the added substance. So the stress in this situation is that we're going to add more of our A right here. So I'm going to say this quite a bit now, but I'm going to say this is my left and this is my right. The stress on this system is increasing the amount of A. I have too much of A and I have to use it up. Therefore, if I have too much of A, I need to consume it, and I'm going to consume it by combining A and B together to form more of C and D. Therefore, the stress on the system of adding more A is going to shift us to forming more of C and D. As a result, the amount of C is going to increase, the amount of D is going to increase, and ultimately the amount of B is going to decrease. Now you might say, well, why is B decreasing? Because in order to make more of C and D, I have to combine A and B together. So we would say in this situation, with the stress of adding more A, our equilibrium is going to shift to the right, and it's going to favor the formation of more products until a new equilibrium point is reached. If the concentration of a substance is decreased, we remove it from the system, the reaction will shift to make more of the substance that was removed. So the stress on this situation is that we are removing B. So I'm going to have a down arrow underneath B. I need to replace B. So this is my left and this is my right. The only way that I can make more B is to go in reverse. And if I go in reverse, that means C and D need to combine together to make more of A and B. So as a result of shifting to the left and making more reactants, my amount of C is going to decrease. My amount of D is going to decrease because, again, those two things need to combine together, going in reverse to make more of A. So A ultimately is going to increase because we're going to add to what is already there and replace the B that has been taken out of the system. And this will occur until the stress is resolved and a new point of equilibrium is established. If the concentration of a reactant is increased, the equilibrium will shift towards the products. We call this a right shift or favoring products. So in this stress, more B is added. So if more B is added, and this is my left and this is my right, that means I am going to shift to form more of C and D. I have too much B, so I need to use some of that B up. A and B will combine together to make more of C and D until a new point of equilibrium is established. That ultimately means that my amount of A that I started with is going to decrease because I need to use some of that A to combine with this massive amount of B to form more of C and D. So to summarize, if more B is added, I'm going to increase the amount of C and D that are produced because I'm shifting to favor products, and my amount of A that was existing decreases. If the concentration of a product is increased, equilibrium will shift towards the reactants. In other words, a left shift. So in this situation, the stress is more D is added. Okay, this is my left, this is my right. My left is reactants, my right is products. The stress in this situation is more D is added to this closed system. So I'm going to put an up arrow over the D. I have too much D. I need to use it up. That means C and D must combine together to form more of A and B and use up some of this excess D. As a result, the amount of A will increase, the amount of B will increase as equilibrium shift towards the left and we form more reactants, and my initial amount of C is going to decrease. Now, this big arrow that you see over the top here, this big red arrow, when you have a stress like this and you have too much of either a reactant or product, that big arrow is going to always cross over this double arrow that you see right here. So if I have too much reactants, we're going to favor products. If I have too many products, I'm going to favor reactants. And that arrow pointing one way or the other will always cross over the double arrow in the middle. Let's do some practice. So the stress on this system is that I'm going to add HF. So this is my left, this is my right. I'm adding HF. I'm going to put an up arrow over the HF. I have too many products. So in this situation, I need to shift my equilibrium to favor reactants, to use up some of this products, And as a result, the amount of H2 will increase and the amount of F2 is going to increase. So the result here was a left shift, and the amount of H2 will increase and the amount of F2 will increase until I reach a new point of equilibrium. Let's look at another example. In this case, we're going to remove F2 from the system. So when I'm removing something, I'm going to put a down arrow to represent removing it from the system. So this is my left and this is my right. Now the only place that I can get fluorine from is from my product side, because here's the F right here. So that hydrogen fluoride needs to go in reverse and decompose. This needs to break down and replace the F2 that was removed from the system. So as a result of that HF breaking apart, I'm going to increase the amount of H2 that is produced, because now I'm favoring reactants, and my overall amount of HF is going to decrease. So this will also be a left shift. The amount of H2 will increase, and the amount of HF will ultimately decrease, as we are trying to replace the F2 that was removed from the system. Let's look at another example. So this is my left and this is my right. The stress on this situation is adding SO2. So where's SO2? Here's SO2. So I am adding it to the system. I have too many reactants. I need to use up some of those reactants and make products, which is why I'm going to put a big arrow over the top saying, hey, we're going to form more products. As a result of that, my amount of O2 in the system is going to go down. Again, why is it? Because I have too much SO2 and I need to use it up. The SO2 and the O2 are going to combine together to make SO3. So as this equilibrium shifts to use up some of the SO2, my amount of SO3 is going to increase. So the result of this is a right shift. As we favor the formation of products, my amount of O2 is going to decrease, and the amount of SO3, which is my products, is going to increase. Let's look at another example. Removing F2 from the system. So this is my left and this is my right. Where is the F2? Let's look at another example. This is my left and this is my right. Removing O2 from the system. Here is my O2 and I'm going to remove it from the system. Now I know it's really tempting to say, oh look, there's O2 right here. I'm just going to use that to replace the O2 that I'm removing from the system. And you can't. We have to have that big arrow, like you see the big blue arrow at the top, crossing over that double arrow that we see right here. So the only place that we can get O2 is from the SO3 on the product side. We're going to shift here to replace. We're going to replace the O2 that was taken from the reactant side by using up some of our products. So as a result, the amount of SO2 will increase and the amount of SO3 will decrease as we shift to replace some of the O2 that was taken from the system. So as a result, this is a left shift. The amount of SO2 will increase and the amount of SO3 will decrease. Let's look at a Regents practice question. Given the equation representing a reaction at equilibrium, we have nitrogen gas plus hydrogen gas gives us ammonia, NH3, in a reversible reaction. What occurs when the concentration of H2 is increased? So what I'd like you to do is stop, take a moment, look at the question, and figure out what you think is the correct answer. Welcome back. Let's see how you did. So the first thing that I would do is I would always put a left and a right, because a lot of the time these Regents questions are focused on shifting left or shifting right. What occurs when the concentration of H2 is increased? All right, I'm going to put an up arrow over the H2. That means I have too many reactants. That means I need to use up those reactants to make some products. So in other words, I'm going to be shifting to the right. So I'm going to cross out anything that says equilibrium shifts to the left because I know I have too many reactants. I need to make more products. The rest of the answers focus on what is happening to the concentration of N2. Well, we know if we have too much H2 and we need to produce more NH3, we need to produce more ammonia, the amount of N2 that is originally there is going to decrease. It's going to go down because we know that the amount of nitrogen and hydrogen need to combine together to make ammonia. Therefore, equilibrium is going to shift to the right and the concentration of N2 is going to decrease because it's combining with the H2 to form ammonia. So if you chose number 3, that is correct. Let's look at another question. Given the equation representing a reaction at equilibrium, POCl3 is at equilibrium with PCl3 and O2. What occurs when the concentration of POCl3 is decreased? In other words, this is going down. So this is my left and this is my right. What I'd like you to do is stop, look at the answers, make a choice, and then come back and see how you did. Welcome back. Let's see how you did. So what occurs when the concentration of POCl3 is decreased? So we are removing POCl3 from the system. That means we need to shift to replace. Therefore, we need to take some of our products and make more reactants. So this is going to be favoring reactants. So anything where it says products are favored is going to be wrong. We need to shift to replace, shift to the left, and favor the formation of reactants. So what happens to our concentrations of PCl3 and O2 over time? If you said that both of these are going to decrease, you're correct, because the PCl3 and the O2 need to come together to form more POCl3. So if you chose number 4, reactants are favored and the concentrations of PCl3 and O2 decrease, you are correct. So what did you learn? We talked about an overview of chemical equilibrium. We talked about Le Chatelier's principle in general. We focused on concentration changes. We did some walkthrough practice and then 2 Regents questions at the end. Need more help? Feel free to contact me. Have a great day.